Hey guys, today we're going to start the last part of calculus that you're going to see in pre-cal, and that is secant and tangent lines. So we have to kind of review a little bit of geometry before we move on and find out this is kind of like our background for what's called a derivative. So the first thing we need to remember is a circle. So when you have a circle and you have a line that passes through two of the points on the circle, this is called a secant line. So if it passes through 2 points on the outside of your circle, you have a secant line. Now if you have a point or a line that passes through the circle on only 1 point, that is what we call a tangent line. And both of these things are something we can use with equations as well. But again, if it's going through 2 points, it's a secant line. If it's just going through 1 point, just a single solitary point on the end, that's a tangent line. So let's look at it in regards to like some algebra and a graph. So if I kind of did what we did when we have our intermediate value theorem, and I look at some graph between A and B. Okay, and what we're going to call down here, we're going to call this time, because this is going to be kind of like a distance time graph. So on my x-axis I put time, and on my y-axis I'm going to put distance. And so I'm going to have some sort of a graph that goes from point A to point B. And it doesn't really matter what it looks like on the inside. Okay, and remember, once I have those points, to find that corresponding y value, I would just plug it into that function. So I'd have this point would be f of a for the y value, and this point would be f of b for the y value. So if I wanted to find something on this graph called velocity, because you know this is just distance versus time, this is how the particle is moving, and I wanted to find the velocity, there are two different ways that we could think about this. The first way is I could find the average rate of change, and if I wanted to find the average rate of change, the average velocity as this thing went from point A to point B, I could use that secant line. Oop, there we go. Hopefully it's a little bit straighter on your picture. And if I wanted to figure out the slope of this line, it's just like what we did back in Algebra 1. We'd find the change in y over the change in x. And so if I wanted to write that out, if I looked and saw the difference between my y values, I could take my f of b, my y2, minus my f of a, my y1, and then have it over my change in x's. And again, you just look at the difference in between your 2 points, so you could have b minus a. So this is how you find the average rate of change. It's the distance over time of a distance time graph. And so this is how you'd find a velocity, or how to find a speed. Okay, so that's of a secant line. And your secant line is going to be your average rate of change. So you're just looking from this point to this point, how fast that I generally go the whole time. Now if you wanted to find an instantaneous rate of change, this is how you spell instantaneous. I struggle with it too. So if you just wanted to find the velocity, say at this point, we're going to figure out a way to do it a little bit better, but today we're going to estimate before we worry about figuring out what that slope is right at that point. Okay? The other way that you might see something like this is if I had a very similar graph, but instead of having A and B, I had T. Okay, so I have this picture where I have something moving. Okay, I got it. Okay, so they gave me T. So I know that the corresponding y value here would be f of t. Now, instead of them giving me this other value over here, say they gave me the difference in between them. So say that they gave me right here delta t, the change in t. So I know how long it went for, but I don't know what time it ended at. Well, it'd be pretty easy to figure out what time it ended at if you know those two numbers, because you would just take t plus delta t. So you take the original time plus how long it took to get there and just add them together to find that middle point. Okay, and then if I wanted to name this y value up here, again, I just plug it into my function. I'd have f of t plus delta t. That's just the change in time. So if I wanted to figure out the slope of that secant line that went from this point to this point, I could still use that same formula where I find my change in my y's over my change in my x, but now that would look like f of t plus delta t minus f of t all over t plus delta t minus my first point t. So one thing to notice here is that your t's on the bottom actually cancel out, and all you're left with is your function value here minus the function value all over the change in t. So it's kind of useful when they just give you the change in and you don't even have to do any calculations there on the bottom. Okay, so that's how you would also find the slope of a secant line. So let's do a couple examples. The first example is going to deal with a table. So they want you to find the average rate of change of this table on this interval with t in between 1 and 3. So remember, this is kind of like just dealing with a distance and a time. So your time will be your x or your t value here, and your distance is your function. And so if they want the average rate of change, they're actually looking for the speed. So you want to know how fast did you go in between 1 and 3. Okay, so all I have to worry about here are those two endpoints. I don't really care about 2 at this point. I just want to look in between those 2 points. And so I just calculate my slope. I'm going to calculate my change in y, or my change in f of t, and then my change in x. So I would have 16 minus 7 all over 3 minus 1, which would get me 9 over 2, or if we needed a decimal approximation, that would be 4.5 whatever, so meters per second or feet per minute or something like that. Okay, so the other thing they might ask you is to estimate the velocity at a specific time, at 3.5. Well, 3.5 isn't on my table, and I don't have that instantaneous piece right there, but I can do an estimate here. And I could find values that are around 3.5, like, for instance, in between 3 and 4, and that would be a good estimate of what's going to happen right there. So all I have to do is do the same thing. I do my change in y, so 21 minus 16, over my change in x, so 4 minus 3, and this is going to be the estimate of the velocity of the average rate of change, the instantaneous rate of change at that point. So my final answer here would be 5 over 1, or 5. Again, you're just trying to find a point that's around there and take those two values and use them. Okay, same deal for finding the velocity at t equals 1. I don't actually know anything about the changing here. I don't know what it was doing at 0. So I'm just going to pick something that was right before and right after normally, but for this one, I can pick just 1 and 2, okay, because that's as close as I'm going to get to estimating. So again, this is an estimate. We're not going to be able to do anything besides estimate between 1 and 2. So using my table, just 12 minus 7 over 2 minus 1, which would get me also 5 over 1, or 5. Okay, so that's if they give you a table. Kind of nice, you look at it, you kind of decide what you're looking for. Now here's what happens if they give you an equation. They want you to find the average velocity, and when they ask you for an average velocity, again, that's the slope of the secant line. It's that formula that we've been using. For f of x, blah, 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 on this interval, x and x plus h. Remember, these are just two x values. So if you were using like your slope formula, this is your first x value, and this is your second x value. So the hardest part here is you've got to find your corresponding y values using this equation. So what I've got to do is I'm going to take my function value for my second point, my y2, so x plus h, f of x plus h, and then subtract the y value from the first one. Okay, then I'm just going to take x2 minus x1. So you're going to notice this looks very similar to the equation that we used on the second graph, the one with the delta t's in it. Okay, so now I'm just going to go ahead and plug stuff in. So I know, just kind of like if I had had something like f of 2, wherever I see an x, I'm going to replace it with 2. Well, now, and wherever I see an x, I'm going to replace it with x plus h for that first thing. So I'm going to have x plus h quantity squared minus 3 times x plus h minus plus 6. Okay, and then this is probably the hardest part here. It's minus this entire function. So please make sure you use your parentheses. You're going to subtract f of x. So I'm going to subtract all of this stuff. Otherwise, some funky stuff's going to happen. Also, if you notice in the bottom, my x is canceled out, which is nice. All I have left in the bottom is an h. So now I've just got to do some algebra. I've got to FOIL this first part out and expand it out. So I'd have x squared plus 2xh plus h squared. Distribute that negative 3. And then right here, I've got to make sure, again, you're distributing a negative 1. So all of your signs inside your parentheses are going to change. So you're going to have minus x squared plus 3x minus 6 all over h. And now we're going to see what we can cancel out, because I already see a couple things. First of all, my x squareds go away. I have my 3x's can cancel, and my 6. So now what I'm left with is just 2xh plus h squared minus 3h all over h. And just like we did with the limits, if you have an h in everything, you can factor out an h. And then you can cancel those out. So your final answer here would be whatever's left over, and so my final answer would just be 2x plus h minus 3. And that's all I've got.